So I'd like to acknowledge my co-author, Chi Shi, who of course did all the hard work. I had a little bit more time than I thought I would, so I added not only the three-way coupling, but one of the other motivations for an application in WaCM, or in a wave and currents mission. So we have...
Okay, so let Mark start again, because it was a bit noisy. So thank you. Okay, go.
He's not going to give me more time, though. We have my colleague Chi Shi, who did all the work on most of this, so I should acknowledge her right off the bat. She's now at the Great Lakes Research Lab, so there's less remote sensing validation than I'd hoped, because she has a real job. I'll talk about her two applications associated with our proposed topics for the wave and currents mission, or something that will be renamed. One of them is coupled air-sea interaction, another one is the transport of fresh water in the Arctic, and a third is the currents in the Pacific. So you've seen two of those already. These are different ones then. So hurricanes are of immediate interest to me right now because we have one in the Gulf. This is the forecast from yesterday. The storm has moved up now, so it's got the higher winds, the hurricane force winds on the coast, and the tropical storm force winds over my home. So every time I come to one of these meetings in France, one of these Gulf storms hits Tallahassee. They almost never hit Tallahassee. They're forecast to go over it early in the projections, but they always move away, but not when I come here.
What does your wife say about that?
She's not happy. She is very not happy. One of the things about these storms is that we're not so good at forecasting the intensity. It just became a Category 4, which was a bit of a surprise because it ended up sitting out over warm waters for a longer period of time. But how warm? A little bit of more warmth makes a big difference in the intensities. And with altimetry, we're not all that great at putting the eddies in the right place. So when we work with currents. Currents are a great way of getting more of the eddies in the right place. There's been a recent study that will come out by George Halliwell and colleagues that in fact uses glider data to show that putting the eddies in the right place helps a hurricane forecast. So this is a clear connection to make now. Another example of getting the eddies in the right place comes from one of these drifters experiments, which you heard about earlier. This was the GLAD experiment with many different types of drifters out in the Gulf of Mexico, and 300 drifters in this case, reporting about every 5 minutes, so excellent coverage. And they were assimilated into the U.S. Navy's coastal ocean model in a 4D VAR system. And this is results from Matt Carrier, who leads this effort at NRL, and many good colleagues. So they assimilated this data, and they ran two sets, one where they didn't assimilate it, and you see the currents for that over here. So these are the drifters. These are the model tracks. You can see, of course, the eddies here, and they don't match. But when you assimilate the currents, they come closer to matching the currents, which is not really a fair comparison unless you do it right. But it does get the eddies in a better position, which is more the point for this application. So for hurricane forecasting, we again think this will be a substantial plus. One of the interesting things about this is they estimate about one observation or one overpass every 18 hours would be sufficient to maintain the eddy information very well. We would get that with a QuickScat-like coverage 7 times out of 8, roughly, at that latitude. So it's pretty darn good if you have that kind of swath, which is what we're suggesting for WaCM. For SKIM, you'll get less coverage, but it's still useful. And then, so that was the one subject. I'll move on to the three-way coupling now. And particularly in this study, we're interested in finding out how the different effects of waves, currents, and air-sea stratification affect the coupling in the boundary layers. We heard many suggestions about these issues earlier. Somebody's saying it's a complete mess. Others saying it's not in the models. So if we put these stuff and try to put them in the models, we get them, and then what happens? And I'm not saying they're right. So there become some caveats I'm going to go over, particularly with the wave interaction. So there's some additional questions which we answered in the process, which are really important for coupled and ocean modeling. So does the atmosphere respond to small-scale changes in the ocean? Because if it doesn't, that makes things very easy for a modeling purpose. Does the ocean respond to the changes in the atmosphere? Again, if it does, and if it's substantial, this could be a really big problem it makes ocean forcing a lot more complicated. Now, larger scales, we know it doesn't. But what about small scales? So does resolution matter? Well, yes, yes, and yes. And the atmosphere does change substantially. The ocean does respond to it, and resolution matters a great deal. And I'll show you that why. So the earlier studies were done on quarter degree or a degree, 2 degree scales, and they didn't find any of this coupling to be important. It's because resolution matters. So we the coupling in these models is improving to the state where it's really worthwhile looking at these issues, and we expect in future weather and climate models that if these things are important, they'll be accounted for. They're moving to the resolutions where that can be done, particularly so at ECMWF and NCAR. So these small scales are arguably going to greatly improve transport both vertically and horizontally, but particularly vertically, which will feed far more nutrients, pump more CO2 up and down, or other gases, it doesn't have to be CO2, and salt transport. It'll also impact the atmosphere. So the water vapor content, cloud cover change, that changes radiation budgets. So there's a lot of interesting feedbacks. Now at the end, I will show you a map, a very scary map of all these feedbacks. So these changes, they could impact global and regional energy and water cycles because of this change to the water vapor in the air, the change in the transport. They'll definitely impact the mixed layer, CO2 budgets, and of course nutrients and fisheries. So they impact quite a few things that people are interested in. So how did we test this? We ran with the COAST model, but John Warner and colleagues, which is a combination of ROMS for the oceans, SWAN, we use SWAN, I was thinking WaveWatch 3, my next project is WaveWatch 3, and WRF for the atmosphere. And this is the earlier version of the coupling. In the newest version of ROMS, it does actually take in the currents as an input. It didn't when we were doing it, so we had to add them. And then we modified the mixed layer physics as well. So we changed the 10-meter wind to be a 10-meter wind with respect to the current. Now SWAN handles that already okay. And in the coupling between the ocean and the atmosphere, we had to have that happen as well, or the ocean to the waves to the atmosphere. And this is what we measure more with satellite as well. So it's a nicer thing to work with, although we really respond to stress. So we added these feedbacks, but this lets us turn parts of these on and off and see how things change. So these are my colleagues on it. She at the top, again, who did all the work, Steve Morey and Dmitry Jukovsky, who are excellent oceanographers and helped me out with that. So what's going on physically? What do currents do? They change the wind shear. So stress is a function of wind shear. If we have a current with winds moving in the same direction above it, it's going to reduce the shear, reduce the stress. If they're going in the opposite direction, it'll increase it. It's a vector sum. You can easily do the math on that. It wasn't a difficult addition. So that's one effect. Now, but if we change the shear, more things happen. So here we looked at the effect of atmospheric stability. And when you reduce the wind shear, you reduce the stress. And what that does is make unstable conditions more unstable and stable conditions more stable. So if you decrease the shear, you're effectively decreasing the wind speeds at 10 meters. The wind speeds aloft, pretend that this is high up here, stay the same in these two cases. Your boundary conditions are the same, but the shape of the profile changes. For stabler air, it's straighter. For more unstable air, it comes down better mixed here, and then is sharper at the surface. So you get to have higher low-level winds in this case, and higher stress. So we're changing stress again that way. And it also modifies wave steepness, as Jerome was saying earlier. So we put this in the model as well in SWAN. And again, I want to move to WaveWatch 3 because it'll run a lot faster if nothing else. And Again, this changes the wavelength, which changes the steepness of the waves, and the stress parameterization we used is highly dependent on that steepness of waves. So all these things are modifying stress, and then of course some of them happen differently in different regions, and it modifies the curl of the stress quite a lot. So how did we set up the experiment? We did a control run, which used normal kinds of forcing, where we just put in a 10-meter wind, ignored the current, stratification was accounted for, and we didn't consider any wave-related variability in the stress. And we did 3 other setups, and I'll look at differences relative to this control. We did another current experiment where we just subtracted the vector current, like I suggested before. This work, we got the same results as a French colleague who did this work earlier. It reduces the eddy kinetic energy by about 30%, which is a realistic result, but not a realistic ocean. We added waves in another one, or a wave-related modification of stress. For those who know stress parameterizations, this will make sense. If you don't, it depends on wave steepness. It's got some problems, but qualitatively, it's a pretty reasonable fit to the dependency on slope. And then we did a 4th model run where we combined both these two in together. So the short answer is that this one doesn't make much sense, and the results don't look good. This one makes even less sense, and this looks like reality qualitatively compared to, this looks fairly similar to that, but it looks a little bit better. We have to quantify that in comparison to some observations. We're still doing that, and again, I apologize, I was hoping to have that. We did not consider Stokes drift, which does add to the impact of waves if we consider that as well. So that's another thing we're doing before we publish this. So this is the difference between the wave and current experiment and the control experiment, and we're looking at stress for our study region off the US coast, the Gulf Stream out here. So the actual stress for the Gulf Stream is much stronger, and it looks very solid if I don't show the differences. And you look at this, and if you don't know what stress numbers are, this seems big and scary, but in fact, the big changes are about 15% of the actual stress. It's not a large change in stress to consider these extra terms on an average of a month. If we look at shorter term cases, of course, it's much larger. Much, much larger. We have the model has much stronger stress gradients on both sides of the Gulf, and you can see that the roughness from the waves, when we look into what causes these changes, has increased by about 12%, which has a fairly low impact on stress overall. It's really the currents that are driving these changes, and the changes in stability that respond to them. Making the stress dependent on the currents has this huge impact on these gradients. And in this case, well, I'll get to that on my next slide. So qualitatively, these stress gradients appear to be slightly more consistent with ASCAT, but it needs more work to say that quantitatively. This is the Ekman pumping, and we're looking again at the same region, and we can see that on each side of the Gulf Stream, now we get the expected upward and downward pumping, and it's much stronger than we got in the uncoupled case. Now, it's so much stronger that in all 3 of the simpler model runs, horizontal advection dominated the energy budgets in these areas. But when we add the 2 waves and currents together, then we get a domination, barely, of vertical, and it's not just Ekman, it's vertical mixing as well. So that has had a huge impact on the energy budget and the temperatures in this mixed layer, which then feed back on the atmosphere. Of course, if you change the temperature, you change the evaporation, which changes the water vapor in the air. So this one has, again, a much greater curl of the stress, much, much greater. And again, it's more like what we see in observations, but I'd like to tell you quantitatively how much.
1 minute.
Yeah, 1 minute. Oh. So what's happening here in the model is that this is a complicated plot, so I'll go through it fast. The dark lines represent a positive shift in the current, and the dashed lines are a negative shift in the current. And then the colors represent the stability, current, or log profile. And what we see is that the current and the stability are roughly canceling each other out. They're the big players. And what that does is we're looking at a 10-meter change in the wind when we look at this. And unfortunately, SWAN takes a 10-meter wind as the input. So these two processes are roughly canceling out the input to SWAN, which is underestimating probably the effect of the waves. Now, we wanted to go in and change SWAN to take the stresses as an input, but the coding is so WaveWatch 3 will switch to where we can do it. Here's the feedback map for the monthly averages. We're looking at a 30-day, the magnitude, I'm almost done, in the 30 days. And you can see some fairly substantial changes. So plus or minus 20 watts per meter squared is a big deal. And the changes in the vertical and horizontal transport. So size matters. Let me do this real quick, and I'll skip the conclusions. This is a 10-kilometer resolution where we have you need 3 grid spaces to get the signal to noise good. We don't get this from space. This is 30 kilometers. We don't get this from space either, unless you're using maybe SAR. This is what we get from space right now. So we're looking at the crosswind component of the wind over the curl, crosswind gradient, wind in the current gradient direction versus the curl, and it's really the key part of the physics driving that coupling. We need higher resolutions to get this. And there's the summary that says what I just said. Thank you.
Any question?
It's more of a comment, really. I mean, what you're getting at here is something that NWP centres are working on actively. I know at the Met Office there's quite a lot of work now to have fully coupled systems down to quite high resolutions. But there's still some way to go. And perhaps what we need to do as a community is to start, thinking and working a little bit closer with some of the modelling communities to get the relevant observation operators that capture these kind of processes that you've got here at the very air-sea interface. Because whatever resolution we give, ultimately it comes down to frictional and then even smaller, where you couple in at molecular layers eventually. So it's a question of the physics is there, but there's a lot that needs to be done to make sure that the models can do the jobs that they are not currently designed to do. If you see what I mean.
No, we had the same discussion at a meeting in April for our satellite mission, and if we can't produce coupled boundary layer models that can work with the physics we're observing, we're going to have a much more limited market. So it is extremely worthwhile to do what you suggest and have a broader community build and test these models. So other things we can do is develop small, cheap field programs to test some of these ideas as well. And that'll go a long way to getting these missions in space and using the data better when we do it. Great suggestion.
But Mark, just a remark. Over the front that you were showing, for instance, with a larger divergence or convergence, you will have a change of the roughness over 100-meter scale. And so this is going to be averaged out. What would you suggest when you go even at finer scale, like you were suggesting? Is that you have very big change of the breaking rates that contribute to the airflow separation and just the stress, and that will be impacting your average. So, or do you, should we stop at a given scale and say 10 kilometers, and then after that what is the limit in a sense?
Well, from an observations perspective, probably 5 kilometers would work well for mesoscale. Some mesoscale is a whole different set of processes. And if you want to get down to those, then you need another set of observations, which Christine was talking about. If you want to model this in NWP, then there's a great deal of smoothing in NWP, and you need to have kilometer scale, almost NWP to capture even the mesoscale, because you're smooth out about 6 grid cells, and you get up to 5 kilometer scale again.
Okay, so after that I have a combined question. So first Yoni, and then...
Yeah, this is more of a...
over there.
Just a suggestion. Having seen this, Mark, it's nice, and And ESA has been very good over the many years to have these long-running projects from GRIST, Global High Resolution SST, Globe Wave, Globe Current. Maybe we should suggest to ESA to consider the Globe air-sea interaction kind of thing to be the next one in the phase.
Globe flux.
Which is true that knowing that the impact of the ocean's color is also impacting the capability to adjust the temperature and color is also transported. So.
Actually, we have a friendly ESA program manager or two for that too. So at least two, I think.
I just want to come back to this discussion you just had about the coupling and what resolution and so on. And just to point out that it's perhaps not happening in NWP, but it is already happening in the operational coastal modeling, where they are running coupled models because they know that if they don't run coupled models, their models just do not give the right results. And they have to do it at high resolution. So perhaps we actually need to start, engaging a bit more with that community of the coastal modelers who are already tackling some of these things and learn their lessons to take to NWP.
Excellent suggestion.
I have a comment which is exactly the opposite. That comment is born from my atmospheric experiences. But I agree actually with Christine that if you have clear forcing by ocean bottom bathymetry, of course you can do fine-scale modeling, and you should certainly do it. But the problem for the winds is in the open ocean that the forcing is not so well determined, but there is still a 3D turbulence. So if you go down with your model to, let's say, that 1 kilometer scale, you find structures that change in time and evolve in time, but we have absolutely no observations to initialize them. So then you sort of start to put in random structures that are realistic but not real, that start to interfere with the ocean. So then the question is, what will you do with those?
When you get down to that scale, you can start pinning down things like entrainment at the top of the atmospheric boundary layer, which would be a huge help in the tropics as well. So there are pros and cons to it, though. You've got the processes in there, but you can't always validate them. So that's where Jeroen's comment about having the case studies and the modeling have to go hand in hand. And I think it's a very valid point.